Hi everyone, I hope you are all safe and healthy. Before we get started with the Metapopulations lecture, just a couple announcements. First of all, there is a midterm exam coming up, the first of our remote midterm exams, and that's going to be on April 15th, which is a Wednesday. You're going to have the whole 50-minute class to take the exam. So everything's going to be basically the same, except you will not be in the classroom as it says here in this website, which I forgot to correct. You will be at home in a comfortable, safe place, quiet place, hopefully. It will take place during our regular class period on Wednesday. So that's 10 to 11 on Wednesday, April 15th. The exam will cover everything from the first midterm. So the material in this course is cumulative. It will include matrix population models, including all of Gatelli Chapter 3, which there should be a PDF of in Web Campus if you do not have your Gatelli book. It will include stochasticity and uncertainty, including both the lecture on that topic and the lab, which was Lab 5. Small population paradigm lecture, the declining population paradigm lecture, the PVA lecture. It will include what we're going to talk about in lecture today and this Wednesday, which is metapopulations and source sink dynamics. Note that the source sink dynamic lecture is due the day before the midterm. Don't wait until the day before the midterm to review that material. So please review both metapopulation and source sink dynamics sometime this week would be great. So you'll have that background and you'll be able to study from those materials. The exam, like always, the exam will consist of a mixture of multiple choice and short answer questions with some definitions at the end. I will host a review session on Zoom on Monday, April 13th. That's 2 days before the exam at 5 p.m. I have set up a Zoom meeting on see Web Campus, the Zoom tab for more details, and it should show up on your Web Campus calendar. And finally, just don't forget that Lab 5 on stochasticity is due at the end of the week, along with your PVA models with written justifications. All right? That is all I have for announcements. So let's get started with metapopulations. Now, this is really quite a new topic. This is not related to topics we've covered in previous lectures. This is really a new topic. And metapopulation ecology really combines what we've been talking about, population ecology, with spatial ecology or spatial processes. So we're putting these two things together, and in doing so, we're able to answer questions about how populations behave in really large spatial scales. And that are the kind of questions that lots of managers and stakeholders and ecologists are interested in knowing about many different species. So this is one of the most dynamic and active areas of population ecology. All right, so what are we talking about here? Broadly, metapopulations are just spatially structured populations. You're going to hear more restrictive definitions. They're out there, and we'll talk about those more restrictive definitions later. But I like to think of metapopulations simply as spatially structured populations. And I think because there's so many different species out there, so many different types of metapopulations out there, it doesn't really make sense to limit the definition of metapopulation. Now that we're considering animals living in particular areas in space, we need to start thinking about movement ecology in addition to just basic population ecology. So in a metapopulation framework, we think about patches or little areas of habitat that can support subpopulation or can support some number of individuals. These patches are connected And the connectedness really involves a process called dispersal. And this can involve immigration from outside a patch into a patch, or emigration, which is leaving one patch and moving to a different one. If there was no connectivity, we wouldn't really be talking about metapopulation processes. There has to be some kind of dispersal among patches. We have talked about the Bide equation in the past. So the Bide equation just says that the change in total abundance for a population that's this delta n, is equal to the total number of births into the population minus the total number of deaths out of the population plus the total number of immigrants into the population minus the total number of immigrants out of the population. That is kind of the full definition of population dynamics. We've ignored immigration and emigration up till now, but now we can start thinking about immigration and emigration. Let's get a little more explicit. In metapopulation ecology, we're generally considering a landscape with a certain number of potentially habitable patches of habitat. We call these patches because they may be occupied, they may have several individuals living on them, but they may be empty. So we have these occupied patches indicated here in green, and then there's one empty patch that's not occupied now, but may be occupied at some point in the future. And so this is our metapopulation, just a bunch of patches in the landscape. Obviously, the patches are connected by some level of immigration and emigration between these patches. And there's a possibility that this empty patch could be colonized by some individual migrating from another patch. So a metapopulation is simply a population of patches. Essentially, we're kind of stepping back and seeing this whole different level of a population. We have not only one population, but we have 2, 3, 4, 5, 6 populations. We step back, and now we're thinking of a population of populations, essentially, or a population of patches. And each patch may or may not be occupied, and different sets of patches may be occupied at different points in time. So at another point in time, this patch might become extinct, and this patch is occupied. So that is really what we're talking about when we are talking about metapopulations. And to make it more realistic, and we can look at a more realistic landscape here and think about patches. In this case, maybe the organism we're thinking of here is a forest-dwelling organism. You really can't have individuals living in a grassy area. So this whole grassy area out here is really non-habitat. And you look at these forested areas, and those represent patches for this individual or this species. We could think of a species that's an aquatic species, and then patches might represent ponds. So for every different species, the way we define patch is just kind of the way we define habitat. That's really just, these are habitat, and everything around the patches is non-habitat. All right. So again, this is kind of a simplistic view of many systems, because in many cases, there may not be a strict boundary between habitat and non-habitat. But for now, that's how we're going to think about this. And that's really how a lot of metapopulation models are really conceived of. It's a simplification that modelers make. So we also assume that all patches are similar. At least for now, we're going to assume, until we start talking about source sink models, we're going to assume that all patches are basically interchangeable. Every patch is the same. So this patch here is the same as this patch here, is the same as this patch here, even though this one's unoccupied. All these patches are pretty much the same. Instead of keeping track of individuals in a classical metapopulation modeling framework, just like Gotelli puts forth in his chapter 4, we don't keep track of individuals anymore. So this is the kind of big difference between this lecture and all the other lectures in this class, essentially. Is we're not even thinking about individuals here. We're thinking about patches. And not just that, all we're really modeling here is the fraction of occupied patches in our landscape. So in this case, we have 6 patches. 5 of them are occupied, so 5 out of 6 are occupied. So the fraction of occupied patches is 5/6. And we give the fraction of occupied patches a particular name. It is F for the fraction of occupied patches. Instead of keeping track of the dispersal of individuals among patches, all we are really thinking about here is the colonization of unoccupied or empty patches. And obviously the process that's causing a patch to go from unoccupied to occupied is immigration. And we'll also talk about the rescue effect, which means that immigration, the process of immigration, can help to prevent the extinction of a patch. So if this patch here is on the verge of extinction, perhaps it will be able to avoid actually going extinct because it receives migrants from here, here, and here, and it never actually goes extinct because of that immigration process. That's called the rescue effect in metapopulation ecology. Metapopulation ecology covers a wide range of scenarios. As long as there are distinct habitat patches in a landscape, as long as there's some spatial structure, as long as there's some dispersal among patches, then it's a type of metapopulation. All right? At least for this class, for the purpose of this class, we have a pretty inclusive definition of metapopulation. When there's a really high rate of dispersal, and therefore the individuals from one patch can mate with individuals from any other patch completely randomly, that is called panmictic. All right, so that's when there's lots of immigration and emigration among patches. But really, I'd still like to call that a type of metapopulation. Just note that in some definitions, including for classical metapopulations, the type that Gattelli talks about in chapter 4, a metapopulation is actually more narrowly defined as a set of patches with limited connectivity and at least some occupied patches at some points in time. So in classical metapopulation ecology, and here we're going to look at this figure which just kind of characterizes different types of metapopulations according to the degree of connectivity from highly isolated to highly connected. And then on this axis, variance in patch size. So from having metapopulations with a bunch of patches that are approximately equal in size to having metapopulations where one patch might be much, much bigger than another patch. All right, and so in a classical metapopulation sense, we have limited connectivity. It's not highly connected, and all patches are similar size and are somewhat interchangeable. That's kind of the classical metapopulation. And in this classical metapopulation, there has to be at least one or two unoccupied patches at any given point in time. Now, those unoccupied patches can change in different years. This patch might become unoccupied. But that's really the classical metapopulation. But in a broader definition, really all of these are just different types of metapopulations. They're populations with spatial structure. I would say that if there's really no connectivity between patches, that kind of stretches the definition of metapopulation. So in this case, this might not really be a metapopulation because there's absolutely no connectivity between the patches. But all these this is a case called the island-mainland model where one patch is much, much bigger and all these satellite patches just receive immigrants from the mainland. They don't exchange migrants among each other. That's called the island-mainland model. And we have the classical metapopulation model here. Here we have a similar metapopulation, but the connectivity is increased, and so we have essentially panmictic metapopulation, where any individual can mate with any other individual from any other patch. and all patches here are occupied. And then we have you can imagine a road going through a formerly contiguous habitat, and now it's dissected a bit, but there's still a lot of connectivity. And so just different types of metapopulations, all of which are very common in nature, and all of which, we should be familiar with how to represent as a model. All right. Although the term metapopulations often used to refer to models where we don't care about abundance, so that is we're only keeping track of the fraction of occupied sites, like the Gatelli chapter, we can, in many models, we may want to keep track of the total abundance of individuals in each patch, and that's perfectly acceptable. We could keep track of the number of individuals in each patch. We know how to do that because we've done population modeling enough to know how to do that. So that's totally possible, and we'll see an example of that in the next lab, which will start on Friday, where we can actually model the abundance in each patch as well as the fraction of patches occupied. All right, now the simplest type of metapopulation model is the classical metapopulation model. This is what Gatelli talks about in chapter 4, and this concept was first introduced by a famous ecologist, Richard Levins, in 1969, and was further developed more recently by Ilka Hansky and others, often with butterfly model systems, but using many other real-world systems. In a classical metapopulation, so patches are either occupied or unoccupied, and we can code that in for our models as 1 for occupied and 0 for unoccupied at any given point in time. We don't consider abundance in these models, so we're totally disregarding a lot of what we've already learned in terms of how to model abundance. Like n has been the primary variable that we're interested in modeling, and now we're not even modeling it anymore. All we're doing is keeping track of whether the patches are occupied or not, and what are the fraction of occupied patches in the landscape. So instead of investigating population dynamics, we're looking at the dynamics at a different level. Like, how does the fraction of occupied patches change? One year you have 75% of patches occupied, the next year you have 60% of patches occupied. That's the dynamics that we're considering now. In the classical model, it's not a metapopulation unless some patches are unoccupied at some points in time. So how does a metapopulation grow? Well, you have maybe just a few percent of patches occupied. How does a metapopulation grow? Well, the individuals from those occupied patches have to colonize unoccupied patches, or you have to have a mainland source, some large source of individuals kind of outside a metapopulation that donates individuals. The individuals have to come from somewhere, and so immigration has to happen to be able to colonize unoccupied sites. How does a metapopulation shrink? Well, certain patches have to go extinct. Certain patches that were occupied have to become unoccupied. And what is the equivalent of demographic stochasticity in a metapopulation model? Well, this one, I'd like you to pause the video and answer a question on Top Hat for this. And the question in particular is this: which of the following statements about a metapopulation is analogous to demographic stochasticity? A, even though the annual risk of extinction for an occupied patch averages 30%, 5 of 10 patches in the metapopulation were extirpated last year. Now, 30% extinction, you'd expect 3 out of 10 patches, but you get 5 of 10 patches in this year extirpated. B, even though the annual risk of extinction for an occupied patch averages 30% in a normal year, the risk of extinction can rise as high as 75% in an unfavorable year. And the key there is unfavorable year. And given the available data, we determined that the average risk of extinction for an occupied patch is between 25% and 45%. All right. So please pause the video and answer the question. All right, so colonization is the name for the process that describes a patch transitioning from unoccupied to occupied. So a patch becomes colonized, and of course becomes colonized through immigration. Extirpation is the name for the process whereby a patch transitions from occupied to unoccupied in a metapopulation. And the term regional or global extinction represents extinction of not just one or two patches in the metapopulation, but all the patches in the metapopulation. More formally, and we'll go over this again in lab, F sub t is the fraction or proportion of patches that are occupied at time t. This can also be known as the occupancy rate. This is the stock. If we're modeling this in Insight Maker, F is the stock that we're modeling. I is the total fraction of patches that are colonized by immigrants per time period. It's can be thought of as a colonization rate, or I'll put in quotes, immigration rate. Immigration, we often think about individuals. I is the fraction of patches that are colonized by immigrants. So I like to think of it as the colonization rate, but Gotelli describes it as, the term is I, which can be a little confusing, but think of I as the colonization rate. E is the total fraction of patches that are extirpated per time period. That can be thought of as an extirpation rate. So if you want to model this stock of the fraction of sites occupied in the metapopulation, all you have to do is take this colonization term, fraction of sites colonized, and then subtract the fraction of sites extirpated to get the total change in the fraction of sites occupied. And a couple more terms to define. P sub I is the probability of colonization for any given patch. So it's kind of like a per capita rate, except by per capita now, we're talking about per patch in the landscape. And P sub E is the probability of extinction for any given occupied patch. All right. So P sub I is for any given non-occupied patch, it's the probability of colonization, and P sub E is for any given occupied patch, the probability that it will go extinct. So we have defined these basic terms, which we'll go over again in lab. Now we can talk through the basic metapopulation models. We will have more chance to go through these models in lab. The basic assumptions of all of these classical metapopulation models is, number one, homogeneous patches. All patches are the same, essentially. Interchangeable. Patch A, patch B, patch C, patch Z in the landscape, they're all interchangeable. They're equal. There's no differences in habitat or anything like that. Extinction and colonization are insensitive to spatial context. So we say in one sense that these models are spatial, but in the other sense, the patches are interchangeable. We're not thinking about differences in habitat quality. We're also not thinking about differences in spatial context. So there's no like local neighborhood effects. The exact location of the patches doesn't matter for these models, all right? So it's kind of an abstraction from reality. We're not really thinking about space explicitly in these models. There's no time lags in these models. That is, metapopulation growth responds instantly to any changes in the fraction of sites occupied. So there's no time lags in these classical models. And there needs to be a very large number of patches. So large, in fact, infinite number of patches, such that even when the fraction of occupied patches, F, is very small, the metapopulation still persists. So that it might be infinitesimally small, but it's still greater than zero. So global extinction is not actually possible in these models. All right, so those are the assumptions that we're making in the classical metapopulation modeling framework. Clearly, this is not super realistic, but it's still a useful starting place. So we're going to start by making these assumptions, and then we'll relax some of them. That is, we'll break those rules at some point. There are several variants of the classical metapopulation model. One variant is the island mainland model, which we've already seen, where you have a huge mainland that donates individuals to the island populations. There's no immigration and emigration between the islands. All immigrants come from the mainland in the island mainland model. And those immigrants are called sometimes, which a term I really kind of appreciate, propagule rain. So it's kind of a graphic way to think about it. You just have this rain of individuals coming from the mainland that is landing on the islands. So it's kind of this external force that it's just, new immigrants are constantly arriving at the islands from the mainland through this propagule rain. And this is the simplest metapopulation model because it means that the probability of a unoccupied site becoming colonized is constant, and the probability of extinction for an occupied site is constant. The second variant is internal colonization. That means colonization can only happen by immigration from within the metapopulation itself. So this time, immigration and emigration only happen between the patches in the metapopulation. So when a small fraction of patches are colonized, the colonization probability is low because there's not that many immigrants. So an unoccupied site has a low chance of becoming colonized. The more patches are colonized, the more chance that an unoccupied site becomes colonized. And so the probability of an unoccupied site becoming colonized is equal to this colonization rate times the fraction of sites that are occupied in the metapopulation. And I here just represents the strength of internal immigration. And another way to think of it is that I, in this model, is the maximum rate of successful colonization of an unoccupied patch when nearly all patches in the metapopulation are occupied. So it's the maximum rate of successful colonization, essentially. We'll go through this in lab as well. The third variant is called the rescue effect, a concept which I briefly touched on earlier. Here, the extinction rate can be reduced by immigration from other populations in the metapopulation. Does it make sense to you how the rescue effect can work? That if there's very few occupied sites in the landscape, then you might have a risk of extinction, a large risk that a occupied patch might go extinct. The more occupied patches there are in the landscape, the more immigrants might be circulating around between the patches, and the less chance that a site might go extinct because there's constantly immigration coming from outside. And we can model then the probability of a colonized site becoming extinct as this extinction, or the strength of the rescue effect, E, times the fraction of sites that are unoccupied in the landscape. So if the fraction of sites that are unoccupied, right, is really high, then there's an appreciable risk of extinction. If there's no sites that are unoccupied, the risk of extinction here goes to 0. All right? And we'll, again, go through this in lab. One key concept is the idea of dynamic stability. In the classical metapopulation framework, extinction it can be commonplace. Extinctions happen every year. Some patches go extinct, some patches become colonized, right? So extinction is kind of a normal thing. Now, we tend to think of it as a terrible thing, but in some systems with small patches, extinction is commonplace, and it's something that can be expected, and same with colonization. And if the extinction and the colonization rates are the same, you're basically at an equilibrium, right? Just like you're at an equilibrium at carrying capacity in a standard population model, the total number of births and the total number of deaths is equal. Here, the total number of extinctions, the total number of colonization events are equal, all right? And we can get a stable equilibrium just the same way. And this equilibrium where extinctions and colonizations are equal, is called the dynamically stable metapopulation. And so the total fraction of sites occupied in the metapopulation remains constant. And there's no conservation concern because this is just the way this metapopulation works. The metapopulation is stable. It's not declining. There's no issue, even though at the individual population level, there are extinctions happening. And this is really no different than the idea of equilibrium that we've already been through. The inputs equal the outputs. In the case of a system population at carrying capacity, any given individual could die, just like any patch might go extinct. But when we look at the whole population, it's not declining and it's not increasing, it's stable. Another important concept is the idea of spreading the risk. In classical metapopulations, we assume a very large number of patches, so there's no real chance of global extinction. But in the real world, as we start to relax the assumptions of classical metapopulation models, in the real world, we have a finite number of patches, and there may be a finite risk of all patches going extinct. So let's think about this in concrete terms. Let's imagine a system where a species occupies a single patch, and there's a probability of extinction of 0.15 per patch per year, all right? A 15% chance of extinction each year. So if there's a single patch, what's the probability of global extinction after 10 years? Well, the probability of extinction for 1 year is 0.15, right? So the probability that the population will persist for 1 year is 1 minus 0.15 or 0.85, right? That's the probability of persistence for 1 year. If we wanted to find the probability of persistence for 10 years, so this patch has to persist for 10 years straight, the way to do that is to multiply that probability of persistence by, the probability of persistence for 2 years is the probability of persistence times the probability of persistence, right? So it's the probability of persistence squared. Here, we're looking at the probability of persistence for 10 years. So that is the probability of persistence to the 10th power. And if we want to get the probability of regional extinction, we just have to take 1 minus the probability of regional persistence. And then we get this idea of this global extinction rate, which works out to be 80%. So let's take a second to go over this in R, all right? So we have a probability of extinction. Here, I'll make this a little bigger. Probability of extinction of 15%, okay? So we define this term, probability of extinction, all right? Here, I can show you. I'll just get rid of these objects. Just read this. So the probability of extinction is 15%, and the number of years that we're going to model this is 10 years, all right? So this probability of persistence is 1 minus the probability of extinction, all right? So if you didn't go extinct, you persisted, and that will produce the number 0.85, so 85% probability of persistence. Now, we take the probability of persistence and we multiply it by itself 10 times to get the probability of persistence for 10 years, right? So the probability of persistence for 10 years is 0.85 times 0.85 times 0.85. Just keep doing that 10 times, and that ends up being about 0.2 or 20% probability of persistence. And 1 minus that is the probability of global extinction, right? And that's 0.8, all right? What if we had more than one population? What if we had 2 populations? This is where the idea of spreading the risk is going to come into play. So now we have 2 populations. Their extinction probability is completely independent. So if one population goes extinct, the other one may or may not go extinct that same year. We compute it completely independently. If we want to understand the probability of extinction for both populations in the landscape. We have two populations in the landscape. We just multiplied this probability of extinction by itself 2 times. So the probability of one population going extinct is 0.15. The probability of 2 populations going extinct is 0.15 times 0.15, or 0.15 to the number of populations power, right? So if we had 3 populations, the probability that they all go extinct in the same year is 0.15 times 0.15 times 0.15. And so we can use this. Oops, I didn't actually run the number of populations here, but 0.15 times 0.15 ends up being about 2%. So there's about a 2% chance that both populations will go extinct in the very same year, all right? And that's the probability of global extinction in a given year. Now we can say the probability of global persistence in a given year, right, is 1 minus the probability of extinction. So that ends up being 0.9775. And now if we take that and we take that probability of global persistence and say, okay, what's the probability of this whole metapopulation persisting for 10 years? We just take that to the 10th power. And that ends up being 0.79, or almost 0.8 of the probability of persistence over 10 years. That means the probability of extinction is 1 minus that, which is 0.2. So just by adding one more population in the metapopulation, we went from an extinction, a risk of global extinction of 80% to a risk of global extinction of 20%. What if we add 5 populations on the landscape? We have 5 populations. The risk of global extirpation is very low in 1 year, right? Probability of persistence is going to be quite high. Then we get the probability of a global extinction over 10 years is still really, really low. It's only 0.0007, effectively 0. So just by having 5 populations in the landscape, we have reduced the probability that all of them will go extinct in 10 years to something that's practically 0. When there was just one population in the landscape, the risk was very high, right? We had about an 80% risk that the metapopulation would go extinct in that case. So more populations, spreading the risk, reducing the chance that everything will go extinct, which is a really important point in conservation biology. All right, one more top hat question before we end this lecture. What if the extinction of one patch was perfectly correlated with the extinction of all other patches in the landscape? That is, if one patch goes extinct, all the patches will go extinct, all right? And specifically, let's move to the top hat question. Imagine a metapopulation with 2 patches, and in which the risk of extinction is perfectly correlated. What is the risk of global extinction over a 2-year period, given that the annual risk of extinction is 50% for each patch? So if one patch goes extinct, the other patch goes extinct. So essentially, you flip a coin and decide whether both patches go extinct or whether both patches are, remain occupied, all right? And you do that for 2 years. So essentially, you flip 2 coins, all right? And what's the risk that the whole metapopulation will go extinct over a 2-year period, given that there's a 50% risk of extinction for both patches, all right? So you flip one coin 1 year and decide, well, does it go extinct or not extinct? And then for the next year, flip another coin, decide whether the metapopulation goes extinct or not extinct. Which of these options gives you the risk of global extinction for this 2-year period? All right. That'll be the end of this lecture, and we'll pick up again with source sink dynamics on Wednesday.